In this video, we are going to analyze one of the most important and concept-rich problems related to the Fourier transform of discrete time signals. In this problem, we are given a signal xn and we are asked to answer several questions about its Fourier transform without directly computing the transform. In the first part, we are asked to find the value of the Fourier transform at omega equal to 0. We know that the Fourier transform is defined as the summation from minus infinity to plus infinity of xn multiplied by e to the power of minus j omega n. If we set omega equal to 0, this expression becomes simply the summation of xn. Therefore, we need to add all the values of the signal over time. Since the signal is non-zero, only from n equals minus 3 to n equals 7, we sum the signal values over this range. By adding these values together, the result is 6. In the next part, we are asked to find the Fourier transform at omega equal to p. Again, we write the Fourier transform as the summation and then we substitute omega equal to p. This gives us the summation of xn multiplied by e to the power of minus jpn. To evaluate this expression, we use Euler formula. We can write e to the power minus jpn as cosine of minus pn plus j sine of minus pn. The sine term is 0 for all values of n. The cosine term is equal to 1 when n is even and minus 1 when n is odd. Therefore, e to the power minus jpn can be written as minus 1 to the power n. Now we substitute minus 1 to the power n into the summation and evaluate it from n equals minus 3 to n equals 7. For example, at n equals minus 3, since n is odd, the value is multiplied by minus 1. And at n equals minus 2, since n is even, the value is multiplied by plus 1. We continue this process for all values of n up to 7. After substituting the actual values of the signal and summing everything, the result is 2. In the next part, we are asked to find the phase of the Fourier transform. To do this, we first define a new signal called yn. If you compare yn with xn, you can see that shifting yn by 2 units to the right results in xn. Therefore, we can write xn as yn minus 2. Now, in the frequency domain, the Fourier transform of xn is x e to the power j omega. Using the time shifting property, the Fourier transform of yn minus 2 is e to the power minus j2 omega multiplied by y e to the power j omega. Any Fourier transform can be written in magnitude phase form. That is, we can express it as the magnitude multiplied by e to the power j phase. Using this idea, we compare both sides and conclude that the phase of x e to the power j omega is equal to minus 2 omega plus the phase of y e to the power j omega. Now, if you look at yn, you will see that it is a real and even signal. We know that the Fourier transform of a real and even signal is also real and even. Since the Fourier transform is real, its phase is 0. Therefore, the phase of y e to the power j omega is 0. And the phase of x e to the power j omega becomes minus 2 omega. In the next part, we are asked to evaluate the integral of x e to the power j omega. We start from the inverse Fourier transform formula, which states that xn is equal to 1 divided by 2p times the integral of x e to the power j omega multiplied by e to the power j omega n. If we set n equal to 0, this equation becomes x at 0 times 2p equals the integral of x e to the power j omega. This is exactly the integral we are asked to compute. Since x at 0 is equal to 2, the value of the integral becomes 2 multiplied by 2p, which is equal to 4p. In the next part, we are asked to find the inverse Fourier transform of x e to the power minus j omega. We recall that if the Fourier transform of Zn is z e to the power j omega, then the Fourier transform of z minus n is z e to the power minus j omega. Therefore, to find the inverse Fourier transform of x e to the power minus j omega, we simply need to find x minus n. To do this, we reverse the time axis of xn. For example, if the signal value at n equals 7 is -1, then at n equals -7, it will also be -1. If the signal value at n equals 5 is 1, then at n equals -5, it will be 1. By reversing all time indices, we obtain x minus n. In the final part, we are asked to find the inverse Fourier transform of the real part of x e to the power j omega. We recall that the even part of a signal corresponds to real part of its Fourier transform. Therefore, to find the inverse Fourier transform of the real part, we need to compute the even part of xn. The even part of any signal is defined as 1/2 times xn plus x minus n. Since we already know both xn and x minus n, we can easily compute this. For example, at n equals 0, both values are 2, so the even part is 2. At n equals 1, both values are 1, so the even part is 1. By repeating this process for all time indices, we obtain the even part of the signal, which is exactly the inverse Fourier transform of the real part of x e to the power j omega. This video covered a very important and practical problem involving many key concepts of the discrete-time Fourier transform. Similar problems are available in this channel, and if you are interested, you can follow the channel and watch more videos.